All right, this should be Video Physics 3.3E, Blake, I think. And this will be available for, probably Thursday, I would say. And here's the wheel I was talking about. This could be any wheel. You know, it doesn't take some effort, some work to push a force times a distance to get it to go around. I could have measured that as a theta times a torque. But since I applied the force at the outside edge, it'd be easier to do it that way. And once I get it spinning, it doesn't want to spin. Once I get it spinning, it doesn't want to stop. So they had to put safety devices on the washing machine, so when you opened up the lid, you know, it didn't keep spinning around because you had the not too bright one-armed housewife that ripped her arm right off, or house husband, I guess. But yeah, they had to put safety devices in the washing machine, so when you open the lid, it applies the brake and stops that heavy wash tub from going around. Page 289. Why would it be beneficial for a bicycle to have a low center of mass when the rider rounds a turn? I have worked that question out a number of times. The textbook answer is the lever arm is shorter when the center of mass is lower, thus the torque on the bike is less likely to tip it over. I have worked this problem out a number of times, that question. And if the bike was this short versus tall, I think what matters is that angle and your coefficient of friction. And I don't think the height of the bike matters 1 iota. So I think the author's got that question messed up. Because I can't see where the height of the bike should make any difference. Regardless of the height of the bike, it's going to be tipped over the same angle, and the force vectors are going to work out the same. So that's my answer to number 6. I guess proved me wrong. Number 7, page 289. A bicycle designer recently modified a bicycle by adding cylindrical weights to the spokes. He reasoned that this would make the mass of the wheel closer to the axle, in turn making the moment of inertia smaller and the wheel easier to rotate. Where did he go wrong? Well, it wouldn't make the rotational inertia less. If you have this much tendency of the wheel to maintain its angular velocity, and then you add weights, regardless of where you add them, you add more tendency to turn, or more tendency to resist changes to the turning. You're going to add more rotational inertia. Now, you will change where that overall value is. You will put that closer to the wheel. We're going to talk about that in a couple of problems extensively with the Fushigi ball. But that doesn't make this less. You're still adding more rotational inertia. If you have rotational inertia and then you put more stuff in there, it's got to rotate. You're going to add more rotational inertia, not less. So that's the answer to the question. Number 8. The front wheel of a penny farthing bicycle was 3 times larger than the rear wheel. I think the farthing is going to be the big one that's 3 times the diameter, and the penny's the smaller one. How much more massive must the rear wheel be to have the same moment of inertia? Well, let's go back a page here. 2 pages, 3 pages, 4 pages, 5 pages, 6 pages, lots of pages, and say that those spokes on the wheel aren't doing much. And so the wheel is pretty much mr squared. And we'll do a calculation with that wheel I just set down. Well, if your I stays the same, then your mr squared equals your mr squared. Okay? So if these are the same, and one of these radius is 1, and one of these radius is 3 times that, so it doesn't matter what unit I measure this in, if it's centimeters or meters or feet or inches or what it is. So I have 1 unit squared here and 3 units squared here. So if one of them has 3 times the radius, that's squared. That's 9. The mass of the other one has to be 9 times the mass. It has to be 9 on both sides to make that work. Because 3 squared is 9. So if you're squaring the 3, the mass has to be 9. Okay, on to some discussion here. I have here on the screen a bunch of moments of inertia, and there's a bunch of moments of inertia in here somewhere. I don't know where they are. Maybe there's not. Maybe there's not a table of them. Here are several that are common. You use calculus to figure out what these are. A hoop is mr squared. A disk is a half mr squared if you have a spinning disk, and it's spinning in the way a disk would normally spin. A sphere is 2/5 mr squared. That mass is even closer to the center of the circle when it got smaller, because we have a 1.5 and a 2/5. Let me get a look here for a second. If your sphere, imagine it's a sphere and not hollow on the inside. If you took a cylinder this size, a cylinder, and shoved it through there, that mass inside of that cylinder would mostly go end to end. But what's excluded from the cylinder is mostly near the equator. So this doesn't have, the mass is concentrated towards the center, I guess is what I'm saying on this. So it's a smaller number than a half. If you have a disk spinning, that mass is evenly distributed through the disk. More of it's farther away. More of this is closer to the center. So the distance on that globe that mass is from the center averages 40% of the way out, 2/5. On a disk, it averages halfway out. On a hoop, it's all the way out to the outside edge. A bar, it depends. If you're taking a baseball bat and you're swinging it by the handle with your hands like this, that mass is more out, it's 1/3 of the way out. You take the length squared times mass and multiply it by 1/3 versus this, 1/12. It's easier to get this to go back and forth versus this. You're easier to accelerate and decelerate. So a bar is 1/12 ml squared for length, but if it's you're moving it in the center, but out on one end, it's 1/3 ml squared. It's the same bar. If you have a shell, and this is more of a shell than a sphere, it's hollow on the inside, a spherical shell, that mass is back farther out to the outside now, because you don't have anything on the inside near the axis of rotation. So a shell is 2/3 mr squared. And there's a whole bunch of these. There's a whole bunch of these. Dropped my globe. And you can figure out all of what you need. So torque is I times alpha, and I could be any one of these or lots of other variations. So for a disk, it's 1/2 mr squared. On the page 291, it says, number 1, a potter's wheel's radius 1/2 meter and a mass of 100 kilograms is freely rotating 50 revolutions per minute, less than 1 revolution per second. So take 50 and multiply by 2 pi, it should be 100 pi radians per 60 seconds. And the potter can stop the wheel in 6 seconds, so that's an alpha. You've gone from 50 revolutions per minute down to 0 in 6 seconds. And pressing a wet rag against the rim and a radially inward force of 70 newtons. Okay, how do you find the rotational inertia of a pipe? Well, that would be a rod and a hoop. I don't know why I have that page there, but okay, on this problem, your omega, your rotation rate is 50 revolutions per minute. Each minute 60 seconds. Every revolution is 2 pi radians, so it's 100 over 60 times pi radians, or 5 pi over 3 radians per second is the speed, angular speed. And you're going to accelerate that. Okay, well, omega finals, omega initial plus A times T. We've got T, we've got these two. So that's 0. This is 5 pi over 3. And it was 6 seconds, so I just divided by the 6 seconds also. So 3 times 6 is 18. And it's negative because you slow it down. And apparently that works out to 0.873. Yep. Okay. So put that in here. And this was basically a disc for this potter's wheel that you you call that throwing. You throw in the clay on there. You throw in the clay on there, and then you're throwing it on the spinning too. So it's a disc. So it's 100 kilograms for that disc. Its radius out is 0.5 meter because it's got a diameter of 1, and you square that times that angular acceleration, and the torque comes out to negative 11 kilograms times meters per second squared times meters, because that's newtons. So it wants you to find those two things. It says something about a radially inward force of 70 newtons. That's kind of irrelevant unless you want to know the coefficient of static friction, because you didn't need it in any of this to stop that. Okay, number 2 we will do later because there's a lab I want us to do first. And then for number 3, you've got the same situation where you're going 98.7 radians per second and you're slowing down to 0 in 2 seconds. So you're breaking a hoop of some sort, maybe a bicycle wheel, bicycle tire. And so you're doing the same thing, it's just not 1/2 mr squared. So you've got the radius, or the mass and the radius is squared, and you've worked out the acceleration. So it's negative 8.1 newtons times meters. And that's where we'll wrap this video up. And probably the next one will be the calculating the, there was 3, 1 and 2, or 1 and 3, calculating the mass of the granite sphere lab.